W Kazimierzu jesteśmy w Waszyngtonie na miejscu marszczyku.
Test. Oh, yep, I'm on. Well, good morning. I'm glad to see all your bright, shining faces this morning. I am going to go the opposite direction as what Carol Stoker talked about. So Carol was talking about a life detection mission for current life on Mars. 2020, this Rover mission, which is currently underway, is looking for ancient life. And I will explain why NASA feels that that is the approach to take, at least for the directed missions and for the mainstream part of the Mars program, as opposed to the competed missions, which are also an important part of NASA's Mars exploration, or exploration in general, because other planets get discovery missions too. But I wanted to also step back a little bit and talk about the programmatic context of why 2020 makes sense at this time. Okay, so as we know, as Dr. Levin mentioned yesterday, looking for life in the universe is hard. And determining if Mars ever had life, either now or in the past, is extremely hard. So NASA has been using the scientific method to try to approach this question by starting out with a series of testable hypotheses that then can be proven and built upon so that the next phase of instrumentation can move forward in a productive fashion and we are not wasting our investment. So the first piece is to first follow the water and then look for habitable environments and then seek signs of life. Now the Mars program for the last 15 years or so has been following this path, and we have reached the seeking signs of life stage, but I want to build up the story so you understand how we got here. So first of all, we have to figure out whether Mars ever had liquid water running on its surface, okay? So and this is that, scientists discover water on Mars. We've heard this headline many, many times. It's getting a little old, right? Okay. Well, the fact is that we started out, we saw evidence of some kind of fluid flowing on the surface, but we weren't sure whether it was water or not. This was from orbit. Then we went ahead and we sent robotic spacecraft to the surface of Mars. In the foreground, you see Sojourner, that was the Pathfinder rover. Then you have Spirit and Opportunity rovers, which were about the size of a human being. And then we have Curiosity, which is entering its third year. Actually, I think it's in its third year of operations at this stage, currently operating on Mars. Opportunity is also still operational on the surface of Mars. So we looked for ground truth. Okay? This is what we call when we can actually go up and touch a rock. I'm a geologist by training, so I like rocks. I like to actually be able to get something in my hand. So, did I hit the right button? There we go. Okay, so Opportunity was sent to follow the water, as was the Phoenix mission. An Opportunity found evidence of past liquid water on Mars. There were layered structures, which is indicative of sedimentary rock being formed. So that is the kind of rock that we get when sediments drift through a still body of water and fall onto the surface and are built up by like a layer cake. Then there were also these spherules that we found. They call them blueberries because they were darker, or they looked more blue than the oxidized hematite on the rest of the dust that covers most of the Martian surface. So these structures had chemicals in them. They had jarosite in them, which is an iron mineral that forms only in the presence of liquid water. So these chemical lines of evidence showed us, as well as others, that there indeed had been liquid water on the surface of Mars sometime in the past. Good. Okay, so then we sent Curiosity. Curiosity was sent to Mars to look for habitable environments. What the heck is habitability? Now, we've been talking about this a bit today, but what I wanted to break it down to you is that you have to have the raw materials, carbon, hydrogen, oxygen, nitrogen. Sulfur, you have to have an energy source, either chemical energy source, sunlight. You have to have some kind of way to oxidize or to try to work through your chemistry. You also have to have this liquid water. It acts as an oxidizing element in the case of life. And then finally, you have to have favorable conditions. Pan Conrad said yesterday that you have to have all these things in the right place at the right time. And I would add to that, for the right amount of time. Because if it doesn't have enough time to turn into life, you're not going to get anything, even if it's there for a brief moment. So favorable conditions means that you have to have a relatively quiescent environment, like a lake, for example, so that it sits and all this chemistry can cook, can work together. Okay? So all of those pieces need to come together. So Curiosity went to an old crater, Gusev crater, sorry, Gale crater, pardon me, it's one of those G's. And in fact, it appears that there was in fact liquid water at some point filling Gale crater. What we saw from orbit were at the bottom, at the lowest level, we found evidence for clays, which are, I think Pan also discussed yesterday, the fact that clays are great for looking for life because they hold a lot of water. They're very good at retaining it, given that crystalline structure. Then higher up, we saw sulfates, and those are also waterborne minerals that are indicative of a changing environment. And then at the top, and I don't know if you can see this, the lighting isn't so great, we have cemented fractures. So it looks as though things were reworked and then the cracks were filled with sediments and glued together, cemented, as it were. So, follow the water, check. Boy, you really can't see that. And then habitability, check. So now we're ready to go be looking for signs of life. And that's where the Mars 2020 rover comes into play. So let me just give you a quick side note, which is that yes, it has a terrible name at the moment. Okay, it's not Spirit, Opportunity, Curiosity, Sojourner. NASA tends to have sort of a standard name for the whole mission. And then as we get closer, the vehicle itself gets named. Okay, so there's pieces of the mission, like on the case of Curiosity, the crane, etc. That's not considered really part of the vehicle. So Curiosity is the rover itself, and I suspect there will be a fancy, fantastic name for the 2020 rover as we move forward. So, seeking signs of life. Over 3 billion years ago, we have evidence for simple microbial life on Earth. And the question is, could it have risen the same time on Mars? Fact is that we see evidence that Mars and Earth were very similar in their environments when life was forming on Earth. So why not could it have formed on Mars? Okay? If we discover that it did not form on Mars at the same time as it was forming on Earth, that will be an interesting clue to the puzzle as well. Okay? Then the question is, what was the differences? Okay, that will teach us something about what really is necessary to find life. So not finding life is, in my opinion, still a useful piece in trying to piece together this whole question of, are we alone in this universe? So the other thing is that Mars is frozen now, okay? It evolved for a period of time and then it stopped. Now we have wind erosion and chemical erosion still going on Mars, but we don't have the wholesale destruction and reconstruction of rocks as we do on Earth, plate tectonics. Okay? What that means is that we have a record of the time that we're missing on Earth. And wouldn't it be great if we could fill in some of those gaps? Now, we do have meteorites that have been returned from Mars to Earth. And those meteorites give us some clues about what might have been going on Mars. However, it seems that the dates of those meteorites appear to be clustered. So they appear to have happened from from just a few ejection events. So they're not indicative of the entire history of Mars. And that's one of the reasons we want to be continuing to send rovers, robotic instruments, and potentially folks to Mars to try to figure out some of these other missing pieces. Okay, so microbial life. What kind of microbial life are we talking about? Well, on Earth, nearly everywhere we look and everywhere we find water, we find life. Okay, and it's this extreme environment type of life that we're looking for on Mars. So we're not looking for little green men. We're not looking for Marvin the Martian. Okay, we're looking for pond scum, little crusty evidence. Okay, but microbial life seems to have a fantastic way of converting energy into nutrients for its use. And so we have photosynthesis that can occur. There is mineral processing for energy in the form of iron and sulfur, and decay of radioactive nuclei are other options. So that's the kind of life that we're looking for, and those are the kinds of chemical signatures that we believe could be in support of life. So now we move to this notion of a biosignature. Okay, a biosignature is an object, a substance, or a pattern that can be created by a life-based process. And so 2020 is going to be looking for ancient biosignatures as opposed to Icebreaker, which is looking for current biosignatures. Okay, so the fact is that we can see structures. We might see chemical reactions or ratios, so that we see things that are out of balance, out of equilibria. That shows that something's been eating something along the way. These are the kinds of things that we'll be looking for. So, okay, enough about sort of the science behind what we're looking for. What about that rover you want to hear? Okay, so goals. First thing to do is to look for habitability. The second, which is that what we call the habitability flower, that petal with the raw materials and the water and the favorable conditions, etc. That's what Curiosity was sent to Mars to do. So the first goal is to go back and find a place that has that habitability. But that's only goal one. Next goal is to do that biosignature detection that we were talking about for ancient biosignatures. And the third objective is to, which we haven't talked about at all, is to put samples into tubes so that they can be collected and brought back to Earth. What, you say? We're going to bring something back from Mars to Earth and it's not a meteorite? Well, that's all new. Okay, so this is the miracle that we're working on for this mission, is to try to get this done properly. And this is challenging because we haven't done it before, and scientists tend to argue a lot. So the fact is that we've been trying to figure out how many tubes, how many samples do you need to understand whether you have life or not, and what kinds of rock do you need to bring back? How many of this type and how many of that type? Well, that's been going on for quite a while, and I will talk about that a little bit more as we go forward. But that is one of our big, that's the big challenge for this mission. And the last one is to prepare for humans. So Science Mission Directorate, which is where the robotic missions, science missions come out of, is partnering with the Human Exploration Directorate to put some instrumentation on this 2020 rover to prepare for the next phase of exploration. So, 2020 is going to be using the same basic rover as Curiosity. And that's helpful because it allows NASA to use the spare parts that are hanging around. In fact, this is one of the high bays at Jet Propulsion Laboratory, and that is the heat shield, the spare heat shield from Curiosity. So that is sitting there waiting for us to be ready to use it. And it also enables us to rebuild some key components because we have heritage here. We know how to do certain aspects of this mission. Okay? So, same basic rover, new instrumentation. That's how this mission is new and different. And that's because 2020 needs to address the new science of biosignature detection, as well as that habitability, which is where you have to start. And the way 2020 plans to do that is to measure the fine-scale mineralogy as well as the elemental composition of these rocks. So fine-scale mineralogy, okay? We've been able to do bulk mineralogy for quite a while, but astrobiologists will tell you, and I play an astrobiologist on TV sometimes, that understanding where in the context of that mineralogy is important. You need to be able to understand the gradient of mineralogy. It's not just about grinding it up, putting it in a shaker bag, and seeing if there's something there or not. So it's not a one-off, a binary decision. It's much more subtle than that. And that's been the issue that we've been struggling and scratching our heads over. You have to have the contextual information. You have to be able to put together suites of samples, suites of rocks. What I mean by it, so you have to have more than one sampling point to really get the story. One sample out of context tells you stuff, but to really get at the astrobiological question, you need that gradient. So I am going to slam through these instruments because all of this information is publicly available and you can find out much more about it, but I just want to give you a taste of what these instruments look like. So this is Mastcam Z. It's similar to the Mastcam, which is on Curiosity, but this one has a zoom lens. So again, trying to get that to that finer scale texture. Next one, sliding right along, RimFax. This is a radar imager, which is going to be able to look beneath the surface and look at the composition and the layering. Okay, detect if there's any ice in particular, so ground penetrating radar for this one. SuperCam. This is an upgraded version of the ChemCam, which was that laser shooting scary thing on Curiosity. So this one has even more capabilities and can do remote mineralogy and chemistry, including organic detection just from the laser desorption. Then we have one of our two cornerstones of the biomarker, biosignature detection instruments. This first one is called Sherlock. This is a laser-induced fluorescence and Raman spectrometer, excuse me, and that will be used to identify the minerals and organic molecules. This is brand new technology that we're putting in space. These have not been flown before in space. So trying to get this to very small size is the key. So Sherlock is going to shine a tiny little dot of ultraviolet laser light, which causes two different spectral phenomena to occur, and then the instrument captures both of those for analyses. Again, you can read about these. I don't want to go into too much detail, but this is new interesting stuff at a finer scale than we've done previously. Next one is Pixel, and this is the other brand new instrument technique, which is X-ray fluorescence at a very, very fine scale. So this one has to be targeted quite carefully. It is, again, it's not for the full, not for analyzing bulk material, but at specific points. So we have to get all this contextual information before we apply this instrument to the location. Okay, so those were the instruments. And now we get to the cache. Here we have different samples of rock that we've cored, and as you'll see, they break up. So there's an issue of how to core these samples so that they are maintained, so that integrity is maintained, so that if there is dust that gets, if the two ends inside the tube rub against one another, make sure, do we get the fines? We don't want to lose all those fines, as they're called. What we want to know is, what happens is you usually get the abrasion at the softer surfaces, and the softer surfaces are actually where we probably think we'll have the life elements, or that's where in those sediments is likely where you're going to find something that's most interesting. So losing those finds would be quite challenging. So the intention now is to go to a location, do some cores, and bring them back, and put them in a safe place on the surface of Mars. And the intention of doing that is because another mission needs to go to actually bring those samples back up to orbit to bring them back to Earth. So these samples, by doing it this way, we allow the time between when the samples are collected and when the next mission goes to decide which samples are worth bringing back. This lets the scientists argue for a much longer time. Preparation for human exploration. So as you've heard over the last several days, the intention is to try to send humans to the Martian system by the 2030 to 2040 time frame. So 2020 is planning on having a proof of concept of this ISRU O2 production, in situ resource utilization. The notion being that we want to make sure that we can do this experiment on Mars with the proper filters, with the proper instrumentation. And then we also have to understand the wind patterns. The dust is one of the most interesting, shall we say, challenges for humans, because it is so ubiquitous and it gets into seals, silicate material in lungs, not so good either. So we have to understand prevailing winds. Are there better times or worse times to be exiting a habitat, for example? Are there times that you should be doing certain kinds of sample collection or not? Those kinds of features will be aided by understanding the weather patterns at the surface. Okay. So we have an ISRU experiment, and I love this acronym, MOXIE. That's one of my favorites. Mars Oxygen ISRU experiment. That's that CO2 to oxygen conversion instrumentation. Oxygen for breathing, oxygen for also fuel, and oxygen to put into water. META, this is the weather station that I was mentioning before. I'm going to keep moving because I'm running out of time here. Challenges facing the Mars 2020. So in 1.5 Mars years, Curiosity, MSL, was able to cover 10.6 kilometers, scoop 2 samples, and drill 6. The challenge for 2020 is that in the same time frame, it's supposed to drive 15 kilometers and drill 20 samples. So this is a challenge, obviously. With the current technology, we're not quite there. So we're looking at ways we might improve. So these are possibilities. We're looking at changing the stereo baseline where the cameras are placed on the rover so that we can see further away and perhaps be able to drive farther. The thing about the way these rovers drive is that they take a picture, then they close their eyes basically and they drive into that scene and hope that they don't fall off the edge. So we don't want them to do that. So if you could actually know that there was a cliff there rather than having to stop and take a picture twice, boy, that would be much better. So we're trying to speed up that kind of processing time. We're also trying to work on hazard detection so that a scene like this, you wouldn't have to go all the way around, which obviously takes more time to traverse, but rather just go right on through. So we're updating necessary hardware. There's been some issues with Curiosity's wheels, and so the wheels are being redesigned right now. And finally, scientists and engineers are working together. We've taken the engineering team out into the field because many of them have actually not been outside of a laboratory. We showed them what real rocks look like, and then they showed us what drilling really looked like and how we were going to try to do that. So it's been an education on all parts. So with that, I'd like to conclude. I've got some links up at the top. Like I said, all of this information is publicly available, and I'd like to open it up for questions. Thank you.
Good morning, Dr. Bass. So I've got a question regarding, first question is, so it's more or less confirmed that NASA is wanting a Mars sample return mission as the follow-up to the 2020 rover? And two, have you decided, or have you thought of the idea of landing a lander for a Mars sample return mission within the proximity of that rover to take its sample collection, because its arm is able to, grapple that sample collection device and put it into something like a rocket and then send it home?
Okay, so 2020 has to be able to stand on its own, and we believe that looking for habitability and biosignature detection, even if the cache, the samples were never returned to Earth, we believe that that is a compelling mission. That is what we've been doing, and we've been finding out all kinds of fascinating things about one of our neighbors. So while we would like to return these samples to Earth, the samples need to sell themselves. They need to be good enough to return. If it turns out that we simply find a lot of boring same old, then perhaps we won't make the investment to return them. And that we leave for the mission to prove itself. The next question was about sending a second rover or a lander of some kind to pick up the samples. So there are, yes, that has been considered. Yes, that is effectively what we're going to be trying to do. The concern there is it limits where the 2020 rover can navigate, because if it's a lander, it has to go to a location that the lander has to be able to reach it. And rovers, so the amount of distance that a rover can travel, what if it gets stuck too far out? So that's a limitation. The next piece of that is having another, you have to design the cache such that another robot can then pick it up, and that also causes certain kinds of limitations. Does it fail with if the 2020 rover were to have a bad day and stop working? Would it fail? Would it drop the cache to the ground? What if it failed in a state where a second rover couldn't pick up the cache? So there's some complexities that have to be worked through with that. Next question.
We have time for one more question, and we will aim to get some from the back of the room later.
Hi. When humans go to Mars, how many samples would they be able to drill in a mission?
Oh gosh. So I work on the robotics side of the house. I really can't speak to the human program and what the astronauts could or could not do. I'm sorry, that's just out of my area. Okay, thank you. Thank you, Deborah.
Na razie tyle, papa, bye bye.